we are going to discuss what's permutation group is. Permutation group. So, for that, first of all, we are going to define what's permutation. A permutation means it's simply a function. It's simply a function from a set of counting numbers to counting numbers. Set of positive integers to positive integers. If suppose n is a positive integer, then set of all positive integer, then f from n to n is called a permutation. It's simply a function. Normally we take for the elements of n as, suppose n, I am going to take, this is the set 1, 2, 3. This, if we take the set, then the function is defined from this is to again 1, 2, 3. So normally we are not going to write in this way. Actually the function is from set of natural number, set of positive natural numbers to another set of positive numbers. Normally we are going to define a permutation as like this. So suppose we have 1, 2, 3. This is the domain and the codomain is like this. 2, 3, 1. This means set of all mapping, this is the set 1, 2, 3. This maps to 1, 2, 3. Again, so 1 maps to 2 and 2 maps to 3 and 3 maps to 1. This is called permutation. So basically the domain and the codomain are the same elements in different position. That's all, because you see that 1 maps to 2, not 1 maps to 1 itself, 1 maps to 2. So the way in which we write is like this. Actually this is written in this form, you know. So now what we say that 1 is going to 1 maps to 2, 2 maps to 3, 3 maps to 1. So this is one way of writing 1, 2, 3, 1, 2, 3. This means 1 maps to 1 itself and 2 maps to 2 itself and 3 maps to 3. So this is normally written as represented as this row 1, row 0. Row 0 means this is like it's an identity. Then row 1 is 1, 2, 3, 2, 3, 1. So this means 1 maps to 2, 2 maps to 3 and 3 maps to 1. And suppose, and row 2 is 1, 2, 3, 3, 2, 3, 1, 2. So this means 1 maps to 3, 2 maps to 1, 3 maps to 2. Again, I am going to write like this. mu1 as 1, 2, 3. Then what's this part? 1, 3, 2. This is another option. 1 maps to 1 itself, 2 maps to 3. I don't know, the numbering is the same. 1 maps to 1, 2 maps to 3, 3 maps to 2. Again, mu2 is written as 1, 2, 3, 3, 1, 2. See, 2 goes to the same point and 1 goes to 3 and 3 goes to 1. Again, mu3 is 1, 2, 3, 2, 1, 3. See, there are 6 maps with the set. There are 6 maps with the set 1, 2, 3. We construct 6 maps out of this set. You see, these are not all the same. These are all different. So now we are going to consider the collection of sets like this. Row 0, row 1, row 2, mu1, mu2, mu3. So this is, I am going to consider a set. That set has the peculiarity that all the elements are map functions. No, these are functions. This is a function. This is a function because this from maps from 1 to 1. So I am going to consider this collection. now I am going to prove that this collection is a group. This collection is a group. Group means, you know that. Group means a non-empty set together with an operation. Suppose maybe sometimes plus is an operation, sometimes product is an operation. So irrespective of anything, I am going to write simply generalize this one, this star. This is called as an operation. So a non-empty set together with a binary operation, together with not an operation, it's a binary operation. Binary operation means if you take two elements from a set, suppose we have a set of 1, 2, 3, set of all natural numbers, if we my G is my set and the operation is plus. So take two elements from this set, 1 and 2. So you get the sum as 3. So 3 belongs to this set. So we take two elements from the set and apply the operation. Again that resultant element should be in that same set. Then we call it as a binary operation. So if you take 1 into 2, multiply these two elements and get 2. If you take the set, then the element is there. So the binary operation means if you take two elements from the set and apply the operation, the resultant element should be in the same set. Then that's what we call as a binary operation. So basically G is a non-empty set and star is a binary operation. That depends on the definition of the operation we define what the operation is. Sometimes it is usual addition, sometimes usual multiplication, sometimes something else we will define. So in olden time, before we say that this sign means 1 plus 2 or simply addition. Now we are defining this addition, this is not. Sometimes this is not 3. So we will define if it is 3, 1 plus 2 is 3, only if this is an usual addition. If it is usual addition, then you will get 1 plus 2 as 3. So if we define something else for addition, then the answer should be different. So basically we have a set G, non-empty sets, and together with an operation, that structure satisfies some condition, then we say that this is a group. That conditions are 1 is associative property. Then 2 is existence of identity, and 3 that's of inverse. If a structure satisfies these three conditions, then we call it as this structure as a group. So we are going to prove that this set is a group. So that means we have to prove 4 things. 1, the defined operation should be binary. Apart from that, we have to prove these 3 axioms too. So once we prove all the 4 items, then we say that this structure, this is a group under the operation that we are going to define, right? So make sure that these things, actually we need all these things. So I want to write everything in a condensed version. So I am going to write everything as, so row 0 is 1, 2, 3, 1, 2, 3, and row 1 is 1, 2, 3, 2, 3, 1, and row 2 is 1, 2, 3, 3, 2, 3, 1, 2, and mu 1 is 1, 2, 3, 1, 3, 2, and mu 2 is 1, 2, 3, 3, 1, 2, and mu 3 is 1, 2, 3, 2, 1, 3. This is what we have the 6 elements. So out of the set, basically we have the set 1, 2, 3. From the set we form these 4 elements. and I am going to consider these elements as row 0, row 1, row 2, mu 1, mu 2, mu 3. So I am going to define an operation here. So the operation is like this one. So what I am going to define a table 0, row 1, row 2, mu 1, mu 2, mu 3, and row 0, row 1, row 2, mu 1, mu 2, mu 3, and form a table. This table is called composition table, and you see, so I am going to define the elements. This is what my operation is called, a composition. So row 0 into row 0, I am going to write it's row 0, and here it is row 1, row 2, mu 1, mu 2, mu 3. So I will show how it happens. So row 0 into row 0 is like this. Row 0 into row 0 is equal to 1, 2, 3, 1, 2, 3, again 1, 2, 3, 1, 2, 3. It's a product of row 0, row 0. You see, 1, 2, 3, 1, 2, 3, again 2 times. So the result answer is 1, 2, 3. The domain should be the same, 1, 2, 3 always. And you see that 1 goes to 1 and again 1 goes to 1. The answer should be, finally this you will get as this. And I will show here what will happen. This is the same. I will show something here. That is, here it is row 1, here I am going to row 1, row 2. The product of these two elements equal to row 1 is 1, 2, 3, 1, 2, 3, 2, 3, 1, and row 2 is 1, 2, 3, 3, 1, 2. This is what the product of, you see, row 1 is this one and row 2 is this one. The product is like this. So the answer should be like 1, 2, 3. You see, the domain is same as I written as the domain. Listen, 1 goes to 2. 2 goes to 1. So 1 goes to 1. 1 goes to 2. 2 goes to 1. So that means 1 goes to 1. 2 goes to 3. 3 goes to 2. So that means 2 goes to 2. 3 goes to 1. 1 goes to 3. That means 3 goes to 3. So this is what the answer. This is how I define the operation. So this is so that way we can define all the elements of this. You can fill all the elements in the table. So finally we can show that using this table we can show that this is a group. So you see, if you take two elements from any of the set, any elements of this set, take the product of two elements, you will get again an element of this set. That shows that the operation is binary. Again, you can prove that this is associativity, and the identity, its identity as this one, and corresponding to every element we can prove that the inverse of every element exists. Every element has an inverse. So finally we can prove that this set is a group. This set is a group. That group is called permutation group. That's called permutation group. Permutation group. This is the term that I have firstly written the board. Permutation. How we get the permutation group. So this is how we prove this system. And now numerically we can prove some problems. Normally for S4 students, normally this will be a question in your exam. So how you define permutation group, and how you multiply, and how you derive the axioms in each and every point, and make sure that this is so easy and you can do while you are while writing the examination. So now I am going to define the inverse of a permutation. Suppose I have some row. Simply I write it as a row. Row is 1, 2, 3, 4. And I define 3, 1, 4, 2. this is how I define, this is the mapping I have. That means 1 maps to 3, 2 maps to 1 and 3 maps to 4 and 4 maps to 2. If I want to find out the inverse, so that is row inverse. So how do we define the row inverse? So normally we have to write it as, suppose we need to find out row inverse. Row inverse, first of all, 1, 2, 3, 4. Every time we write it as the domain as 1, 2, 3, 4 itself, whatever be the given number given. So I write it, even for row inverse, I write it as the domain as 1, 2, 3, 4. You see, this is all 1-to-1 mapping. So this means 1 maps to 3. For row inverse, 3 maps to 1, 3 maps to 1, 3 maps to 1. 2 maps to 1, that means 1 maps to 2. So 1 maps to 2. 3 maps to 4, then 4 maps to 3. So 4 maps to 2, it's 2 maps to 4. This is how we define the inverse of a function. So normally they will ask some questions, how to find out the inverse. So sometimes they will give row and they will ask some questions. So there is, if there is a sigma like this, 1, 2, 3, 4, then 2, 5, 1, 4, 3. So I define like this. So they will maybe ask to find out a row. Your row is this one and sigma is this one. They will ask the question like this, find out sigma, row inverse sigma. So you got to find out, you have to find out what's the row inverse and you multiply this with the row sigma. So you will get an answer. So normally they will ask in your examination for S4 students. Another thing is, sometimes instead of this, they simply write, 1, 2, 3, 4. Sometimes they write this is simply as this. This, if they write something else like this, no, I am right, some row is like this. This means, this is actually this 1, 2, 3, 4. This means 1 maps to 2, 2 maps to 3, 3 maps to 4, 4 maps to 1. Sometimes for this, in your question paper you saw a line like this, that means this. That means this is the map. You have to write the domain as 1, 2, 3, 4. You see, 1 maps to 2, then 2 maps to 3, 3 maps to 4, and finally 4 maps to 1. This is how we define. Sometimes, for this, so I am writing another thing, some row, another way of writing row. So I will write it as sigma. Sigma is written as 2, 4. Sometimes they are written as 2, 4. So this means 1, 2, 3, 4. So 2 maps to 4, 4 maps to 2. The others are the same. So this is how we are defining the map. Sometimes they will ask sigma is only 2, 4 means you have to write the domain as 1, 2, 3, 4 and 2 maps to 4, 4 maps, 2 maps to 4, 4 maps to 2. The others are same. This is how we define permutation, and normally the questions are like this when they take the product and composition table, all that. So S4 students has to make sure that they have a very good idea regarding these permutations so that they can easily get mark. So this is how we teach and this is how we present all these things. So make sure that you should have a very good idea. That's all.